Hello, today we will discuss rank nullity theorem. The statement of rank nullity theorem is, let U of f and V of f be two vector spaces and T U to V is a linear transformation. Then if U is finite dimension, then dimension R of R of T plus dimension of N of T is nothing but dimension of U. Here R of T means rank and it is nothing but null space now. Now here I am taking first of all now, what is a U? It is a finite dimension vector space. Now N of T is a null space. Therefore first of all I am taking, and one more point, N of T is subspace of U now. Now I am taking N of T base set. What is the base set of N of T? Here I am assuming S equal to, that is alpha 1, alpha 2, dash alpha k. It is a base set of N of T. Now here this set contains k elements. Therefore dimension of N of T is nothing but now k. Okay. And one more point, N of T is subspace of U. Therefore, as per base extension theorem, we can extend this base up to U. Okay. Now therefore, the B equal to, B is nothing but now extension base of S. And it is a base for U now. Now here all alpha values and additional values, that is theta 1, theta 2, like that, theta m now. Now therefore here we have k alphas and m thetas now. Therefore dimension of U is nothing but now k plus m. Okay. After that I am taking now one more set now, the images of this one, these values now, that is nothing but now B1 it is now. And we know that these all alphas are belongs to a base set of N of T. Therefore I am now taking this all alphas now, only thetas now, that is T of theta 1, T of theta 2, just it is a set only now, T of theta m now. It is just one set. We are assuming there is a set B1 now. We want to prove that the B1 is a base set of R of T. If any set is said to be base set, the set should be satisfied two properties. One is the elements should be linear independent, and next linear span property now. Now first we want to prove the B1 is nothing but now linear independent set now. If any set is said to be, if any vectors are said to be linear independent, first you write in the linear combination form, that is T of A1 into T of theta 1, A2 into T of theta 2, and AM into T of theta m. And this all linear combination is comparing with 0 bar. Now here T is nothing but linear transformation. Therefore as per the property, we can write T of A1 theta 1 and A2 theta 2 and I dash AM theta m equal to nothing but now 0 bar now. Next term. Now here complete the value equal to 0 bar. T of some vector equal to 0 bar means the vector is satisfying null set property. Okay, the image of this vector is 0. Therefore the vector belongs to null space now. Therefore here A1 theta 1 and A2 theta 2 and next AM theta m is an element of belongs to N of T. What is null space property? Alpha belongs to U and alpha belongs to U and T of alpha equal to 0 bar, such elements are belongs to n of t now. Null space. Those elements, all are those elements are belongs to null space now. Now here also it is an element of null space now. And we know we have base for null space now. It is a base set. Therefore you can write the vector as a linear combination of base elements now. Therefore a1 theta 1 and a2 theta 2 and dash am theta m, it is the vector which is belongs to n of t. Now we are expressing the linear combination of its base elements now. That is b1 alpha 1 b2 alpha 2 dash bk alpha k now. And take one side now, total values, that is b1 alpha 1 and b2 alpha 2 and the next bk alpha k and the next a1 theta 1 and a2 theta 2 minus dash minus am theta m is nothing but now 0 bar now. Now observe here we have all alphas and all thetas. Actually these all alphas and all thetas are belongs to B, which is a base set of, it is a base set of U now. And it is a base set, that means the elements are already linear independent. That means the coefficients all values are equal to 0 now. Therefore all B values and all A values are nothing but now 0. They are nothing but now zeros now. Therefore all B values zeros and all A values zeros. Here we want only A values are zeros. Therefore all A values, that A1, A2 and AM and etc. are all zeros now. Now therefore here T of theta 1, what are the vectors? T of theta 1, T of theta 2 and the next T of theta m. These are linear independent vector now. Vectors all are linear independent vectors now. Now therefore one of the property is a completed. Now it is a linear independent set property is completed. Now we will discuss second property now. What is the second property? L of B2 should be equal to R of t. It is the second property. Already we know that it is if two sets are equal means one must be subset of A subset of B and B subset of A, then only you can say A equal to B now. Now here I am taking one element, beta belongs to R of t, okay, and there exists one element vector alpha belongs to U such that T of alpha equal to beta. They are like that. Now alpha belongs to U. Here we are assuming there exists one particular element satisfying this relation, that is nothing but alpha. When alpha belongs to U, you can write alpha as a linear combination of its base elements, base vectors now. Therefore alpha equal to C1 alpha 1 and what are the base elements of U? All alphas and all thetas now. Now therefore C1 into alpha 1 and C2 into alpha 2 and the next Cm Ck into alpha k and the next D1 into theta 1 and D2 into theta 2, D2 into theta 2 and Dm into theta m now. Now I am applying T of alpha. T of entire this value, this linear combination, that is C1 alpha 1, C2 alpha 2 and the next Ck alpha k and D1 theta 1 and D2 theta 2 dash Dm theta m now. T is nothing but linear transformation, therefore we can write C1 into alpha 1, C2 into alpha 2, and next Ck into T of alpha k, and next D1 into T of theta 1, and D2 into T of theta 2, and next dm into T of theta m. And we know that these values T of alpha 1, T of alpha 2, they are nothing but now zeros now. Why they are zeros? They are belongs to null space elements. Therefore exactly C1 into 0 and C2 into 0, and next Ck into 0, and the remaining values D1 into T of theta 1 and D2 into T of theta 2, and continuation dm into T of theta m now. Now therefore it is nothing but now D1 into T of theta 1 and D2 into T of theta 2, and dash dm into T of theta m now. Now therefore this value T of alpha value, it is nothing but now beta. Therefore it is a linear combination of T of theta 1, T of theta 2, dash T of theta m now. Now therefore it is a linear combination form. Therefore you can write T of L of B2 is nothing but now R of T. It is a property now. Now therefore B2 is satisfying both properties. One is it is already linear independent vectors, and now it is satisfying linear span property. Therefore B2 is nothing but now base set of R of T, and therefore the dimension of R of T is nothing but now here B2 having m elements, therefore it is nothing but now equal to m. Therefore that is the theorem concept. What is the concept of the theorem? Dimension of R of T plus dimension of n of T equal to u, and it is satisfying now. Okay, thank you.